For the introduction, I need to repeat some parts of what Fabian explained before, and then I would like to introduce the modeling and the mode identification software that we use called SUMCON. Then diagonalization of sensors and actuators. And then I will show some measure transfer functions of the real system, and then I will talk about some requirements, local control, the damping of the resonant frequencies stage by stage, and then how with these local controls are we meeting the requirements or not. So first, let me remind you what the type B suspensions are or where we use them. So it's used for the beam splitter, for the SR2, SR3, and signal recycling mirror. Well, this whole arrangement is the signal recycling. So we have a pre-isolator part or top part, which is a top filter or filter knot with an inverted pendulum. We have a gas filter chain, which is the standard filter, the bottom filter, and well, we can also include the top filter. They are all for vertical isolation. And apart from that, we have the magnetic damper that I will also talk about this one later. This is to damp the first mode, the low frequency one. And we have the payload, which is the intermediate recoil mass, the intermediate mass, and then the optics surrounded by its recoil mass. So what do we use to model the type B suspensions and some others? Is this software SUMCON, like it's written in Mathematica, and it has been developed by some people like Takanori Sekiguchi, Mark Barton, and so on. So what can we do in this software? So for example, if you have a PAL that is very good in Autodesk Inventor, you can have all the masses of your system and the suspension point and the geometry of your system and include it here. Also the moments of inertia, or you can also measure this of your system and include it here in the software. So what can you do with SUMCON? So one of the features and one of the things that it's useful for us is that we can get the transfer functions for a given force at a degree of freedom that we have an actuator, or we can also have the transfer function for a ground motion if we have the profile of that ground motion at the site. So once we have all of this, we can construct the model, and we will have like a calculation result. So from those calculation results, we can get like this window, and also we can get something with the eigenmodes. So we will have a list of eigenmodes, and it will show us like how the suspension move and at which frequency. So within at least the 100 hertz, the suspension shows 44 eigenmodes. So we can also, for example, we can also click here on more, and we can have the eigenmodes individually, and we can take a look around the suspension. So these are, for example, the eigenmode number 1, number 2, and 3, and the number 7, for example, which is the inverted pendulum rotation. 45, yes. So I can see 45 here, but I can actuate only on 15, where I have my actuators. Yes. Yes. So I will show the transfer functions a little bit later, but first I would like to talk about the cross coupling of the inverted pendulum stage now. So of course in the software it all works very nicely, but in the real system we have cross coupling. So it will not be like pure translation, or longitudinal motion, and this will not be only rotation. So we need to take care of the sensors. But first, as Ettore and Fabian said, we need to add more mass here in order to achieve lower frequencies. So we need to first work out the mass that we need on our inverted pendulum, and then we need to take care of the actual position. So this is a cross-section view of a type B system, for example. So we are looking at it from the top, and this cross-section will show us our actuator and our sensor. So we cannot just say the sensing and the actuation is happening in the same part. So we need to take care about this. So before going on, I would like to show this, like what is our analog world and our digital world. So this is happening basically like in the computer part, and this is happening in what we can see, not inside the computer, for example. So we have like our set of electronics that we use to measure the signal that comes from the OSM, for example, that Fabian mentioned. And these are located somewhere in the suspension, at some points at the suspension. We can measure some points of it, and we will have we will have access to some degrees of freedom. So, but after we measure that, we need to include some filters. We need to work out the matrices of the local coordinates to have sensor or actuator vectors, and we need to include our control filters, and so on. We can have the actuation force. Okay, so what do we do for diagonalization? So we need to start with one of them, and we actually need to go to the system and check this experimentally, like to measure either the actuation or the sensor location, and then we can calculate for example, if we start with the sensor matrix, we will work out the coil actuation matrix. So we believe that this one is located in a good position. So what we do, for example, here, we excite the system at a single frequency, each of the coils, and we will read out how the system behaves for that frequency. So you need to be a little bit careful about that, because that frequency shouldn't excite any of the resonant modes of your frequency. So you need to find a gap, or it could be a very low frequency, like 10 millihertz, for example, or you could find a gap and do it like at 3 hertz, 4 hertz, and we actually did that at 3 hertz. So, okay, now you have diagonalized your inverted pendulum. But also, for example, I have diagonalized this one. I will skip and this part of the vertical isolation or vertical control, and also that one. But I would like to focus now on the optics. So the suspended optics, which is beam splitter, signal recycling 1, signal recycling 2, signal recycling 3, or signal recycling mirror, is suspended by the type B suspension, right? And we are interested in the longitudinal motion, pitch motion, and yaw motion, rotation. So how do we do that? With the optical lever that Ettore explained before. So in the ideal case, this optical lever, which is hitting the suspended optic, the signal recycling SR2 or SR3, then it's hitting a steering mirror, and we would like to measure the pitch or the yaw here with this QPD, the quadrant photodiode. So with this one, in theory, it will be easy to get the real motion. And with the length sensing optical lever, like as also Ettore explained, you can put this one in this. You can put this QPD at the location of the image plane of this convex lens, and you will be only you can get um, your system will be sensitive only to longitudinal motion. So that is what you do. For example, your R here will be the distances 1, 2, and 3. And for length sensing, will be the distance will be 1, 2, and 4. And your D in this shows in D, for example, the image plane. We can get this, that it will be sensitive only to longitudinal motion. If there is another document that is well explained here, if you are more interested. But in reality, longitudinal pitch and yaw are all cross-coupled, as well as we saw it before with the inverted pendulum. So we need to diagonalize as well these three motions. So what are the origins of this cross-coupling? Let's say like our steer mirror is disaligned. So that is going to cause mainly a pitch to yaw coupling. And now let us say that we are not hitting the QPD right at the starting point. So that is going to have a longitudinal to tilt. Another example, if we are not hitting the suspended optics at the center, so that is going to have a tilt to longitudinal, and so on. So taking into account all those mistakes that we have done, for example, or we could have done, we need to try to arrange these values in order to reduce the coupling. So we can do that looking at the transfer function, or we can do that looking at the time series, for example. So I will explain this one. So longitudinal to pitch coupling. So how do are we going to check whether the longitudinal is coupled to pitch? We move the inverted pendulum in longitudinal that we have already diagonalized, and we will see how the mirror is moving in pitch or in longitudinal. So we can see is coupled to pitch here. So now, doing this arrangement in our matrices, taking into account all this, we can decouple the movement in pitch. So these are the transfer functions of the system. So now that our measurements, we believe that our sensing is right, we can take some transfer functions of the system. So these are all for the inverted pendulum, for example, and the orange is the measure, and the purple one is a fitting of this curve. So this is what Fabian explained, that this is the noise from the actuator. So we will just ignore this part. So therefore, same here for the phase. So we can do fitting in zero pole and gain, and this will help to design the active filters later. So I'm showing also for the intermediate mass, and some more for the mirror itself, for the suspended optics in longitudinal, pitch, and yaw. So now the sensing is ready. So now it's possible to measure all the transfer functions of your system, and with that you can say whether the system is healthy or not. Like whether you need to go and actually replace something, study there is any possibility of some parties touching the security structure or something like that. But if you are good here, you can just go ahead and start a commissioning. So what does it mean? So the commission means to make work all the subsystem separately somehow, and then make them all work together in order to run the interferometer. Okay? And then the performance, is the system meeting the requirements to run the interferometer or not? So, for example, we have some requirements in the countdown phase, which is when like the starting point of the interferometer or after, for example, a shock or a kick or an earthquake, for example. So we have this requirement that the decay time of all the eigenmodes should be below 60 seconds. So we can improve the duty cycle of the interferometer. And then at the log acquisition phase, we have the RMS mirror velocity below 0.5 micrometers per second, and the angular fluctuation should be below 1 microradian. And then for the observation phase, we need to have low control noise at 10 hertz and so on. So we need local control. So for example, if we have with our system, very basic system, we have the equation of motion by a Laplace transformation. For example, we can put it here in this control loop, and we need to study here the transfer function of this control loop, and we can write it in terms of poles and zeros that we did with our transfer functions. So now we need to study stability of the system. Because, for example, if this product is -1, we will have an unstable system. So what do we use for local controls? We use position control and damping control for the tower. That means for the vertical isolation, for the vertical isolation systems, the gas filters, and also for the inverted pendulum. And we only use damping control for the payload. So this is what we are using in the tower, and this is what we are using in the payload. So as an example, if you are using these two filters for your tower, let's say it's an example of the signal recycling 2 mirror inverted pendulum and longitudinal. Your control for the tower in this case will be like this, and your system, the transfer function of that degree of freedom is that one. So you need to study the product of this one, of the control and your system. So that means you need to study the open loop transfer function and see if when this product is 1, whether it has 180 degrees of phase shift or not. So these are parameters. For example, this is phase margin. So you can say like this system is how close or far away this system is from instability. So once you have your control loop closed and you think your system is stable, you need to measure the decay time of this 45 or less between the. You need to concentrate in one frequency band, and you need to measure all these decay times. So I would like to talk first about the first mode, which is at this frequency of 54 millihertz, and this one has a quality factor. That means it will have a long decay time. So this project was done by our summer student there, and to damp this torsion mode, that is only passive damping, and it's done with this eddy current damper. So basically, we need to get this current damper, eddy current damper, close to this copper disc, and we need to measure how the mirror will move. So for example, we got these results, and we can say like the frequency measured, it was 55 millihertz, and therefore the eigenmode is identified, and we can check that the decay time of this mode is below 60 hertz. So this is coupled with many other modes still. So yes, so I mainly diagonalize the top part with the lowest part, but still I have some some not, there is still some degrees of freedom that couple from the intermediate mass that is not well diagonalized yet. Oh yeah. Uh, Sorry, what is your question again? Yeah. And oops, sorry. Yeah, that's also true because you cannot like isolate this eigenmode from the motion of the higher frequency in other happening in other parts of your suspension. That if the this another stage of your suspension is also vibrating at a different frequency, will couple to the so yeah. Mhm. Mhm. Yeah. So this rest of this emotion is because the suspension is still moving in another stages. So in order to reduce, I mean, what we want here is to identify this mode, at least in this part, and be sure that that this one is the decay time is below 60 seconds. So this is a note that there are some other eigenmodes shown in the simulation, and but we are not measuring them because we have not either we have not access to them by sensors and actuators, but most of these modes are not important for the purposes of the interferometer. Let's say for the same for this same eddy current damper, we don't really care whether that is moving too much or not because that will not basically will not affect too much the mirror. So we need to plot all a summary of this is a summary of the decay times of our system, for example. So these are the first 34 eigenmodes, and this is undamped in orange, and this is damped in blue. So here are two that they have still a long decay time. So we need what basically what I would like to emphasize is like you have your control and you think your control will work by simulation, or you think your control is stable, but then you need to go and measure your system And then if you are not meeting the requirement, you need to go back and redesign your filters and work out a better filter. And then, for example, here you can, with your software tool, you can identify which frequencies are here. Well, yes? Yeah? Ah, this one. That one? Yeah? You mean for example, the coil magnet actuators that they are in the suspension here at the last stage? Ah, yeah, yeah. Yeah, well, basically, it's to dump this first wire torsion that we call it. But yeah, it will dump also the pendulum mode. I see. I see. I see. Yeah, I think we we have not measured that one. Mm. Yeah. Okay. Yeah, we have some requirements, but not as strong as for the test masses. Um, yeah. Uh, mm, mhm, mm. Did you- yeah. Mhm. Ah, I think that was test in Tama, right? Mm, mhm. Ah, I see. Mhm.
Damp, damp, Damping actuators might be, for sure, they're always not perfect. They aren't perfect. But digitally, you can perfectly balance them. While in this case, you cannot correct.
No, but for example, we characterize, I mean, we measure ones with one suspension, and we try to follow the same for the others. And I'm measuring at least that the decay time was below.
And you decided, okay.
Yeah.
Thank you.
So, yes. So some eigenmodes that are over our requirement, we need to go and redesign our filters. But I would also like to show some RMS angular fluctuation. Well, this is measured with our OPLEV. So with the OPLEV, of course, has a lot of noise, but at least we can show that the RMS motion is small enough, and then if we want to measure it better, we can switch to the interferometer sensor or signal and check this better. But what I want to show is, like, if we close the loop only in the inverted pendulum, the angular fluctuation of the pitch, what we can measure here, it goes from 10 to 1 microradian, and the yaw goes from 24 to 1.18 microradian. But for example, if we close the inverted pendulum plus the intermediate mass control loops, we go from the initial one that from 10 microradians to 3.3. So we are injecting some motion. We are exciting some motion of the mirror with these controls, and that one is, well, it could be only sensor noise, but let's say this one is 0.4 microradian. So what I want to say here is, like, with the IP control, we are getting close to our requirement acquisition phase. But then when we close another loops, this one we are not meeting the requirement, at least for pitch, but for yaw, yeah. So at this point we have to go back and tune our control filters again, and we need to redesign the damping filters in order to integrate the signal recycling suspensions to the main interferometer. So this is the work ongoing, and this is my last slide. And what the people is doing also is the diagonalize of this part of the intermediate mass, and include the signal from the geophones. Like Ettore said, we need to have an inertial damping. And the controls, yeah, we need to include this inertial damping using the signal from the geophone, and also including the coupling cancellation filters or hierarchical control filters. So this is what is going on now. And these are the references of this content. If you are interested, please, you can ask me, or you can take a look into these theses or documents. Okay, thank you.
Questions?